Hi, good afternoon, everyone. My name is VENKATESH RAMANATHAN. I am a director of data science at PayPal. Forget to put the typo in the slide. This was earlier presented in another conference, and I had trouble getting the latest slides here. I'm going to be talking about graph-based representation learning to prevent payment collusion fraud. At PayPal, we work on, we are basically a machine learning shop, building machine learning models for a variety of applications. Fraud is being our primary MO. We also build machine learning models for credit approval to marketing to estimating the value of our consumers to predicting most valuable consumers from our data set. So today's talk is mainly going to be on the fraud side of things. So I briefly explain, elaborate more on how we tackle fraud at PayPal at a very high level, and dive into some of the machine learning algorithms we apply to detect fraudsters. And I'll share some early results from some of the experiments I did and conclude my talk. Okay, PayPal, we have been an established machine learning group for over 10 years. Earlier, the way we will traditionally been building machine learning models is using robust feature engineering. So you have this raw transaction data, you engineer features which discriminate fraudsters patterns from good users patterns. So we have a very sophisticated feature engineering group. They look at, from a fraudster's angle, we have a team of data scientists, analysts, and intelligent analysts, financial analysts, and so on, look at the fraudsters' behavior and try to predict and stay ahead of them by feature engineering aspect. So once we build the features, we build machine learning models. Traditionally, we used to build simple linear models using logistic regression and so on. Later on, we had a single layer neural network, a nonlinear model to ensemble model like gradient booster trees, and now we are more into deep neural network and other more complex models to detect the fraud behavior. We have like hundreds, close to thousands of models for a variety of applications, and even to detect frauds at different levels. So we have a variety of models, and in order to build not only a training infrastructure, we also have to have a prediction infrastructure. When a payment transaction goes through, we want to detect fraud in very short SLA, less than 10 milliseconds or so. So the way we do it, we have a highly scalable inferencing prediction infrastructure as well, in addition to the model training infrastructure, which is typically we do model training in an offline environment. In a Hadoop ecosystem, we have the data there, but the prediction happens in more on an online stack. We have a variety of Java and C++ stack to facilitate the prediction portion of it. As I already mentioned, we have a huge team of data scientists and researchers, financial intelligence analysts to build our machine learning pipeline. So we detect frauds at 3 levels. Essentially, at the transaction level which is where we want to capture when a bad transaction goes through. Before even the transaction goes through, we want to detect the fraud. So that's at the transaction level. That's where we employ advanced machine learning techniques, but we also have a constraint by the SLA. We want to not only want our good customers to suffer, we want to push away our good customers by having a higher SLA. So we have more sophisticated models after the transaction goes through as well. At the account level, we monitor a variety of account-to-account interactions, and this is where we typically do money laundering activities and so on. That's done at the more, we have well-established profiles of bad behaviors, which we have data collected over 10 years worth of data set, where we have built profiles. We understand our good users and bad users' behavior to detect frauds at the account level. At the network level, we have even more sophisticated models to do a lot of money movement activity, bad money movement activities, and so on. Obviously, fraudsters are constantly adapt their traffic patterns, reverse engineer whatever models is tend to capture and try to evade that. Still, obviously, one way to stop all the frauds is you shut the system, right? So, but then we won't be in the business. So there's a trade-off between how do we let the good users go through, but still have very keep our loss low in our payment transaction. So we need cost-effective solutions that can model these complex patterns, but also stay ahead of the fraudsters. How do we do that using a more scalable and computationally efficient prediction models? So one of the specific type of fraud is called collusion fraud, which is where my recent focus area is. This is a simple example. Presume that we are all good people here. So example, but don't get any ideas from this. So, buyer purchases an item using PayPal. So we all have used PayPal. So buyer purchases an item. Seller ships an item to the buyer. Buyer finds the box empty and asks PayPal for a refund. PayPal can refund the buyer. So in most cases, we have a buyer protection. No questions asked. Most buyers actually get the money back if they are unhappy with the purchase. In this case, they didn't find any shipment in the box. So no questions asked from the buyer. And PayPal, we try to still resurrect the money from the seller side. That's where we work more closely with the sellers to resurrect money from the merchants instead buyers go scot-free. The seller gives proof of purchase. In this case, they did mail the shipment, so they have a proof of shipment label, so that they give it to PayPal. In most cases, PayPal also provides seller protection. So because we have seller protection, we have to pay the money back to the seller. Effectively, in this is a lossy transaction for us because we can't resurrect from the seller and the buyer got the money. So in this case, assuming that PayPal seller and buyer split the money. So this is, you can see the buyer and seller are colluding to ship an empty box. So we call it empty box problem. So we have several cases where, buyers and sellers collude together to steal money from PayPal. So obviously there could be many such buyers and sellers, and how do we detect such buyers and sellers who constantly stay below the radar? For example, if amount is less than the certain dollar value, it's more cost ineffective to have a lot of this back and forth with the merchants and so on. So they try to keep it below the certain radar and make small purchases and still commit fraud at PayPal network system. How do we detect such buyers? Could be they are doing two types of business. So one of the cases actually you can have if you have a consumer account, you don't pay any fee, but a lot of cases, PayPal customers establish a consumer account but conduct small businesses within that in the scheme of consumer network. So we don't. So that way, other way, they're exploiting the payment infrastructure. There could be many such as they could also, once we detect certain bad behavior, they could create newer accounts and move from IPs to IPs and accounts to accounts to evade such our protection system. How do we detect such buyers and sellers at scale? You can imagine that if you were to plot all this, the buyer and the seller and the IP address and the shipping address as different node elements in a graph, this could be more efficient to tackle these kind of frauds using a graph-based approach. So that's a goal of this particular research. So let me dive into some of the algorithms level. So traditional machine learning, if people are not familiar with it, there is a significant effort spent in human feature engineering. So you have this raw transaction data. You want to build features, for example, let's say that we call it something called velocity variables. You could say that number of transactions which happens in 2 hours, 4 hours, 8 hours, 30 days, and so on, right? Those are called the velocity variables. You create a whole bunch of these features like this. Typically, fraudsters, you'll have certain type of fraud patterns. You're going to have very high velocity. They are trying to break into our system or conduct many transactions in a very short amount of time, which a normal user won't do it, right? So that's sort of a feature which differentiates between a good and a bad behavior. So these features are actually engineered as a human thought of it, and human engineered these features over a period of time. A significant effort is spent in feature engineering aspect. The other where a lot of human effort is spent in the labeling aspect. How do we detect whether a particular transaction is a typical machine learning model? Even today, most machine learning models are supervised. That means you need to have a feature vector and you need to have a label whether it's a fraud or not fraud. And you train a model using these trained data set and use this model to actually predict future transactions. The labeling aspect, whether it's a fraud or not, at the transaction level, it's not trivial, right? So you're looking at a transaction alone, it's not easy for us to label it. So you need a significant amount of experts to looking at past transactions, previous transactions, looking at our profile metrics and so on to detect transaction as fraud or not, so that we can use for a training pipeline. So labeling and the feature engineering is still significant human effort is spent. But what deep learning is powering is something called the end-to-end learning, where you take this raw transaction data, you directly skip the feature engineering aspect. Instead, you learn features automatically using an algorithmic approach. So the deep learning is actually been extremely successful, mainly because of this. It not only eliminated the human intervention of even image processing and all those things, where all the features has to be engineered manually. Now you don't need human to engineer features. So deep learning power that automatic feature learning aspect of it. But still the labeling is manual. So on the labeling side, how can we actually automate it? The labeling aspect of it is something called a lesser known technique, but it is extremely useful, and we found it a lot of beneficial is active learning. I'll go a little bit more on the active learning aspect. Is that the idea behind it is you start with a small labeled sample and use a machine learning approach to model you want the human to label a transaction or good or bad. So you want to give only the transaction which the model is confused about. And this is a model is certain about fraud or not fraud. You don't give those data samples for the human to label. Instead, you'll give the ones which is confused about. So the active learning is kind of a semi-supervised way to reduce the burden on the human for the labeling aspect. So the new approach is how can we automatically learn features with minimal human intervention, and how can we apply active learning based approach so that we have a less burden on human labeling aspect. So specifically for this particular, we still have all those raw transaction data. Transaction data is not only transaction. You can think of when you log into the system, log out from the system, sign up for the system, making a payment transfer. Those are all event level raw transaction data. We use those data we still have expert engineered features. One of the underexplored area is a feature representation from a graph structure. So that's what I will dive a little bit more into, that you take learn additional features from a graph structure and combine these features and use active learning for the labeling aspect. And it specifically used driverless AI, which open source product called H2O. They have a product called driverless AI where they have various algorithmic implementation of machine learning algorithms to do the model development aspect of it. So specifically on the graph-based representation learning you can think of it as you're all familiar with the social networks is as graphy data, and also you have Internet of Things and so on. For us, we have transaction level data, credit level data, all this data we can actually we have these data represented in a graph structure. How can we learn a representation? Essentially, before you build a machine learning model, you need to create the features, right? And the features has to be, you can think of it as an Excel table with the columns representing the features and rows representing the training example. How do you feed these graph structure to a machine learning algorithm? Almost all machine learning algorithms are trained to consume only tabular data. How can we create these feature representation from a graph structure to a traditional machine learning pipeline? So the graph-based representation learning is exactly a technique to actually learn a feature representation. So how it learns a representation, there are several algorithmic approach, matrix factorization and random walk and graph neural networks. The more upcoming one is using graph-based neural networks. So for this particular talk, explored some technique using random walk. So the idea behind is graph-based representation. A specific technique I used is something called a node-to-vec, which is actually a researcher from Stanford, Grover and Leskovich. This idea comes from this technique called word-to-vec, which has been extremely successful in the NLP space to have learn a vector representation from words. So node-to-vec is how can you learn a vector representation from the nodes of the graph, so which means that the edges were not considered for this particular, so you just learn a representation for the nodes. When you're learning a vector representation for a word, so one of the thing is you can look at, there are techniques is that how do you predict what the next word or the adjacent context words is given your target word, or the other is given a context word, what do you predict the target word is. In a NLP case, you can look at some kind of you basically feed in a whole corpus of text data, and you can use something called a sliding window approach. You can look at words before and after to basically find out all the neighbors for particular words, and if words are similar in meanings, they will co-occur together in a lower dimensional space. So how do you apply the same technique to graph structure? That's what this node-to-vec is about. Essentially, the idea behind it is that in order to find the neighbors in a graph, this is actually not a contribution, it's a contribution by Stanford researcher as reference attributed here. But the idea behind it is that in order to learn a representation for graph node elements, you not only want to look at neighbors who are directly connected, which is actually a local community neighborhood, but you also want to look at neighbors who are far away. There could be neighbors who are far away. For example, if you take an example of an airport hub, right? So Chicago is an airport hub for United Airlines, and Frankfurt is airport hub for Lufthansa. Both Lufthansa, the Frankfurt and Chicago are basically functioning as a hub in an airport network, right? So these, if you want to learn a representation, if you learn a representation for these airline network, you should get a similar vector representation for both Frankfurt and Chicago. That's the idea. So it's not only they are directly connected, but they could be far away, but they have a similar representation. So this is actually, you can think of it that the fraudsters are not going to be sitting together in the network, right? So it could be distributed all over the network. How can we, not only if we know behavior of certain fraudsters in a local neighborhood, how can we predict similar fraud patterns in our payment network structure? So the idea intuitively, it does make sense. So the way it explores is basically a random walk approach. So in order to, it's basically solving a maximal likelihood estimation function, and it's trying to optimize using a well-established optimization algorithm called stochastic gradient descent. You cannot explore the entire graph because it's going to be computationally inefficient. In order to make it computationally efficient, it uses a random walk approach. It starts with a node with a given probability. It looks for the neighboring nodes, and it uses a combination of breadth first and depth first search to account for not only the local community structure, but also the nodes which are far away from this. In this case, U and S6 are following, having the similar role, so you should, after the optimization function, the representation learned for U and S6 should be very similar. That's the idea behind it. So for the active learning approach itself, so once we, the feature learning from the graphs was done in an unsupervised way, but still the models are, where the fraud models were built using a supervised machine learning approach. That's where I think active learning. So active learning, I already talked about it. Essentially what you do is you take a very, very small labeled data set, you build a robust model on the labeled data set, and you have a huge pile of unlabeled data set. You use this well-trained model to label an unlabeled data set. whichever data points it is confused about. In this case, let's say fraud probability is between 0 and 1. 1 means it's a fraud, and 0 means it's not fraud. If the probability is close to 0.5, that's what the model is confused about. And those are the data points you want to give it to the human to label it, so that we can add more data points to our label data set and iteratively build a bigger and bigger data set to build your better model. So let me skip some of this technique, but the several strategies behind it. But a couple of things I would say what is specific of active learning specific to fraud is obviously in fraud the data is very highly unbalanced. So let's say you are doing active learning for image processing, right? So image processing also you need a labeled data set, whether it's a dog or a cat on the picture. But that you can outsource it. You can give it to Amazon Turk, and you give a few, a human can actually visually look at it, and they can label whether it's a dog or a cat. And even if there is abuse in that strategy case, if majority are on agreement, there is indeed a dog or a cat, so you can use a majority voting strategy to decide, okay, that's indeed the label for that particular image. So fraud is actually, you can, you need trained experts to detect whether a particular transaction is fraud. So it can't be outsourced just like other cases. And fraud is time consuming, so you need to look at transaction before and after. It is extremely time consuming effort. Fraud labeling requires data from several entities, so you don't want, if you want to look at the account level, that alone is enough. You need to look at the IP addresses they used and which locations they are buying from, what sort of goods they are buying from. Are they buying digital goods? Well, that's where they commit to most of the frauds, because it's harder to track versus tangible goods. Those kind of things you need to go back at other entities to determine whether it's a fraud or not. And the key important thing is fraud, the tag, which is actually whether it's a fraud or not, the maturity takes time. For example, in a credit card fraud, right? So chargeback happens after you find a transaction which you are not happy with, that you file for a chargeback. By the time you get the money, it's about 2 to 60 days or so. So it takes a longer time to for the maturity to happen. So that's not the case with the other domains. So there are lots of challenges with applying active learning to fraud case. So essentially this is giving you a high level implementation architecture. We have all these raw events, everything is sitting in our huge Hadoop cluster. We have Hadoop and Spark ecosystem. One other thing which didn't exist before this work is that most of the HDFS you cannot, it's not amenable for doing large graph processing or applying graph-based learning technique. So we imported the relevant data, which are graph structure, into a GraphDB and apply node to vector on top of it, so that the GraphDB is extremely useful for, because you can index the data, you can learn feature representation on a subgraph versus using the, or learn different representation on different subset of the graph also. You can iteratively do this learning process much more quicker if your data has been stored sitting in a GraphDB as opposed to sitting in HDFS. So once you learn the feature representation, we use also the expert engineer feature vector. So our fraud models are been there for a very long time. So it's been extremely, it's very hard to get even a 0.1% improvement on the performance. So we don't want to eliminate our existing feature space. We want to learn additional feature space or additional logic which you can incorporate into our models to detect fraudsters better. So an active learning was used for the labeling aspect, and I used driverless AI for model training. Experiments, these results were subset of 1 year, typically we use 4 or 5 years worth of transactions data to build most of our models, and the graph is slightly smaller, but now after this result I expanded to 20 billion edges and so on. So the implementation architecture is highly scalable, node to vec. So the way we scale, so you can think of the Hadoop HDFS as more of a scale out infrastructure. So you add more nodes to your network, it scales out. Where our model training and the node to vec, those are all built on the concept of scale up approach. So you have a fewer highly powerful machine with many cores. GraphDB, we have petabytes of. Also, we use specialized storage. specialized, a lot more memory than the typical this thing, and a lot more CPU cores. And for model training, we use GPU. So it's more of a scale-up approach. So rest of the stack is actually more of a scale-up model. So we are kind of somewhere between scale-out for our data processing and batch processing and so on, but most of the model training and other aspects done in the scale-up infrastructure. So these are the tools, and this is used for this work. So H2O, so this is actually results, just to give you, we don't build models in laptop, but just to give you a comparison of computation time. So what it takes about 2 hours to get a accuracy factor of 1 with rival SAA, you get it 21 minutes using GPUs. Obviously, you must be using or familiar with the GPUs, because GPU is extremely computationally efficient for a lot of machine learning algorithmic exploration. Okay, so this is AUC is a measurement final metric. With the combined graph-based representation features and using active learning, the AUC we were able to improve by 3%. Just to FYI that this is not the metric we use. Internal metric is different because you can get a very good AUC, but there could be no fraudsters or no bad transaction that amount, right? It's because it's highly unbalanced problem. But we have an internal metric where we were able to see close to 3% improvement in our measurement. So final conclusion. So I think this is graph-based representation is really an emerging area. So you can think of the success of deep learning is mostly in the deep images and natural text data. How can we actually bring the power of deep learning to a more structured data? And graph is a structured data. How can we leverage that? So certainly, I think graph-based representation is showing promise there, specifically to do more complex fraud detection. We use extensively active learning. We are also exploring active learning for even to train, let's say that we have trained a model on a graph structure. How can we do graph-specific prediction problems like a node classification, link prediction, and so on? For example, I'll give you an example. Let's say we look at our graph structure. From the IP address, we want to know whether this IP address belongs to a business. Right? So it's not evident from just getting a geo lookup or whatever. You won't get the right representation. Is it a business? Does it belong to an educational institution? Because we not only look at that particular node, we also know the nodes which are connected to in what type of activities we are performing. We can make those predictions whether that particular node is of specific type. So that is extremely useful. For example, let's say if you know that something is shared across a household, and if it's a household IP address, we can, if we enable transaction for one, we can also enable transaction for others in that household too, right? And also, like, other cases I was saying that where you could be operating as one business to commit crime and the other business to commit good behavior. So, those kind of things, mixed use cases, we can identify better with graph-based representation learning. So the next step actually, so this was exploration was unweighted graph, and want to expand it to subgraphs and so on. The other temporal changes, the way we do temporal changes, the graph structure changes all the time, right? So right now it's more of an ad hoc approach. We retrain our model every week to learn the temporal evolution, how much our graph has changed from week to week, and use those, feed that into our machine learning pipeline. But how can we learn that directly from by applying a time component to the edge, so automatically learn this feature representation, which takes into account the time dimension. That's a challenging work which we are currently working on. Graph convolutions and geometric deep learning is much bigger area of how can we learn automatic features from the graph structure is area which is actually emerging research area, but also worth promising. That's pretty much a talk and acknowledgements to all these vendors we work very closely with on this work. So I think time for questions. Happy to answer.
Is it working? Yeah. So in the You mentioned you have a year of data and then 3 months for the test, so that's a year and 3 months for data. And you mentioned the fact that you're using active learning to not label all these transactions for a year and 3 months. What percentage do you actually manually label for your active learning approach?
Yeah, so typically I would say that, this experiments are 1 year and 3 years of the data set, but we have several models all expanding 4 years for the just to FYI that we use a longer time window as well and much bigger data set. Typically you would want to, different types of fraud, I would say about 20% of the transactions you need some kind of labeling, because even today, in order to build a machine learning model, you need labels. So, 20% is what I would say, because it varies between certain complex fraud versus obvious fraud. So, but on average, 20%, I would say. Okay. Yeah. So because we have close to thousands of models. So. Some models are like we have some kind of automatic way to refresh our models. So let's say that that which is kind of done close to daily or within less than a week, because we have when we know the obvious frauds where we can just by taking a newer snapshot of the data set itself, we could get some boost, which rapidly we can refresh our model, which has been done in an automatic fashion. The ones where with the more complex frauds, where a model deteriorate, that I would say about 3 months to 6 months. So. Typically, the newer problems always you take 6 months even to define the problem, what kind of data set you need. So newer ones, I would say 6 months. But the fraud problems, I would say about 3 months, mainly because in most fraudster cases, we need to relook at why some of the behavior has changed to analyze and inspect and come up with crafting intelligent features to capture those patterns. So typically, it's about 3 months. Yeah. So we have a research organization. My particular thing is computer science research. So we have a team of researchers. We always look at several techniques to, is not by accident. There are a lot of techniques which it doesn't work as well, right? Yeah. So this is actually an exploratory work. So not all. My personal passion is academia. You can think of it as far ahead in the research area, but the academia's focus is let's publish papers, and there is a different KPI or whatever, right? Industry is too cautious in adopting some of the state-of-the-art techniques easily because of the scalability challenges and so on, right? So my goal is what are some of the feasible techniques from the academia research? How can we bring it closer to the industry? So in this case, NoteWork was published just last year, for example, right? So it's an academic research. So I always look at what are the academic research which are practical in nature, which can it actually solve some of our problems. In this case, it did work. So for some of those techniques, actually, one of the things I'm looking at a graph convolution. There are challenges in applying graph convolution. It's because it's a emerging research area. So I still don't have tangible results from the graph convolution technique. But NoteWorks seem to yield the results. So it's more of a research effort. Some 50% works and 50% fails, and so on. So.
Really good talk. I was just curious, how computationally expensive is it to compute some of these features? Because I'm guessing if you build the whole graph on a year's worth of data, right, that's a massive graph. Right. But any particular day, the transactions you're looking at are a very small subset of that. So could you comment on that?
Sure. Yeah, of course. NoteWork actually, first of all, I think you need to have we are looking at the entire thing as not at one layer. We are looking at the full stack replacements. For example, when Google published the MapReduce framework, so buy a bunch of commodity servers, laptop, put together, and you build a Hadoop cluster. Yeah, okay, you scaled out a model, right? That doesn't quite work when you want to push to the next level. I think some of the challenges that for the computers, you need to have the right infrastructure, right? So what we have seen is the GPU is giving an extremely computational bandwidth for us to explore more, exploit more, so that we, because the whole machine learning is a lot of hyperparameter optimization, you explore a lot of parameters to build the best model, right? GPU is certainly giving us that compute horsepower to explore more. So, right, for the node-to-vec itself is built as a more of a scale-up model. So it is not GPU-based, for example. It uses CPU, but we have close to 200, we have the state-of-the-art Skylake with 220 cores and so on, so we have many of those. So within under a day, we could actually train a node-to-vec model for like 3 years worth of transaction data. But the key thing to keep in mind is that when you are doing any graph-based learning algorithm, you don't want to put non-graphy data in a graph structure. Like for example, HDFS, right? Let's just throw in anything you want. We will build a schema on read, so we can put all the crap in there into HDFS. Let's worry about consumption later, right? So that kind of model won't work when you're applying graph-based learning. So what we have seen is that ingesting the data of graph structure into a graph DB, then applying graph-based learning algorithm on top of it seemed to be computationally efficient. So within a day, we were able to train a models of our PayPal-sized transaction graphs.
So my understanding is you have a lot of features using existing tabular data.
Correct, yes.
Then you using those tabular data apply to the graphic DB, apply to node-to-vec, and build a new data set based on existing data set. Right? Then you based on your learning, active learning on those, you think you improve 3%, right?
Yeah. So essentially, yeah, we are not at a point we can completely eliminate the human engineered features. So we are not nowhere close to that actually, but we are going in that direction. So yeah, that's it. Oh, that's right. Actually, I couldn't hear. Could you be a little bit louder? So.
I guess do you find redundant features between what human engineered features and features?
You are asking if there's some kind of overlap or? Yeah. Oh, okay. So I don't know if you see the top 50% in the 100 variables we were learned using the automatic feature learning aspect. So, which means that if you do a relative ranking of all the feature space, the human engineered features ranking were pushed down with this particular approach. So, we do see value in that, but we cannot eliminate 100. So, the 500, 600 variables, there are still 450 human engineered features sitting there actually. So, the relative ranking got pushed down for sure with automatic feature engineering. So essentially, you can think of it like, I gave you the velocity example, right? Human have only fixed functions they can think in their mind. For example, if you want to construct a velocity function, I want to create a feature which captures number of transactions per hour, per 24 hours, right? What this automatic feature is that let's learn the time dimension automatically from the data rather than using fixed functional form, right? That's what is fundamentally eliminating it. So human can think of only fixed functions and fixed mathematical formulations, but from the data, let's learn that actual dimension. What should the time dimension should be from the data rather than, so I think I'm time's up. So, but thank you very much for everyone, and I'll be there after the talk, so feel free to grab me. Thanks.